Lesson 13, final lesson. Okay, and we're looking at two things: the Geiger-Muller tube, okay, it's detecting radiation or Geiger counter, and a little bit on spectroscopy. In both cases, we videos following on, and especially in the spectroscopy case, the video gives a clearer example than what I will be giving you on paper on the page here. Okay, so Geiger-Muller tube. So what we have is we basically have a metal cylinder. Metal cylinder, okay, and we have a wire anode in the middle. The metal is the cathode, the cylinder is like a can of beans with a wire stuck up the middle of it, okay, and that's a wire anode. The wire is important, okay. There's a bit of insulation here to stop the cathode and the anode touching, and then you have basically a power supply here. We just do plus minus, and you have something to measure the current. So we call it a rate meter, or you could call it an ammeter, and that goes back to the cathode. Okay, that's the wrong way around. So that should be the minus, and that should be the plus. Plus connected to the wire anode. Right. So what happens? Okay, quite simply. Okay, and this is a mica window through which like the mica windows in the X-ray tubes. That's through which the radiation can go. Okay, so we have radiation coming in here. Radiation is ionizing. Okay, and the ionizing radiation ionizes this gas. So we have a gas at low pressure, generally argon, in here. Okay, okay. So the radiation comes in and ionizes the gas. It ionizes into positive argon ions. So we just put them as plus, and they're attracted to the cathode. And negative electrons, so just say E. Okay, and they're attracted towards the wire anode because it's positively charged. What happens is, as they get close to the wire anode has what we call a very strong electric field. Okay, so around it, a very strong electric field. So the electrons go faster, faster, faster. They hit more argon atoms. They knock them out as well. So as the electrons go in, they're causing more and more and more argon ions and electrons to be produced, and it's a bit like an avalanche in a mountain, so it's called an avalanche, a gas avalanche. Okay, so you get more electrons down here than you'd expect, and the electrons give you the pulse of current. That's how it works. Okay, the more ionizing it is, the greater the current, and you get your click, 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 as you may have seen in Chernobyl or things like that if you watch them in the movies. Okay, that's how it works. Let's have a look. Okay, I have one here. It stopped working many moons ago, so this is it. Okay, we can't actually break it up very, very well, as it turns out. But if I take this out, okay, right, this is effectively what's going on. Now that there is is this guy. Okay, that's effectively the Geiger-Muller tube. Okay, so the outside of it is the cathode, so it's just a metal, as you can see, metal cylinder. And at the front here, okay, you can't really see it very well. Okay, that's the mica window. So it's just a window there. That's the mica window. And here then, where the insulation is, okay, that's where the wire anode is. So I can take that apart, and you can see the wire anode there, okay, and that continues down into the middle. Now I've tried to take that apart and have failed, okay, but you have the idea, okay. That's what it is. It's put into this little posh, okay, and then it doesn't work anyhow. So there you go. That's it. That's your Geiger-Muller tube. That's connected. Where's God? That will be connected here, but it's connection to a rate meter. Okay, that's the Geiger-Muller tube. Okay, so second thing we want to look at, video on that later. Okay, second thing we want to look at is spectroscopy. Now, spectroscopy, okay, something. This will work a lot better when we're back in school. So we'll be going back on this. We'll do a few classes on this when we get back. But let's have a general idea. Okay, if you remember. When we were getting the wavelengths of light, okay, let's remember the experiment that we did. Okay, we had our screen, okay, and we had our grating, and we had our light here. Now, if you remember, if we use red light, we got white light in the middle, and then we got a red dot here, n equal to 1, n equal to 2. But remember, if we had red light, if we had white light, what we got, white in the middle, but here, we got a spectrum, and here we got a spectrum. So spectrum here, spectrum here. We get loads of spectra. Now in spectroscopy, we're just interested in one of those spectra. So look, all we're interested in, okay, if I can find a better colour, all we're interested in is one of those, okay? And in this scenario, okay, if we're using white light, it's basically what it probably is a metal, okay? So like your traditional light bulb was a metal that heated. Now, in a metal, it's very complicated inside it. And in a metal, you know those energy levels we were talking about for emission light spectra? For a metal, there's an infinite number of them, a huge amount of them. So every possible energy is possible. Every possible energy a photon is released. So you get all the colours, because every energy is a different colour. You get all the colours, so you get your full spectrum. You get your rainbow, okay? Red, orange, yellow, green, blue, indigo, and violet, okay? Right, okay? That's what you get, spectrum, okay? Now, that's fine. So for a solid, which is very complicated, and all those different the electrons can fall different amounts, huge number of different amounts, you get every colour possible. But if you have a very simple little thing, okay, like a neon atom, or a mercury atom, or a sodium atom, you only get a few. There's only a few different electron falls that there can be. So there's only a few different colours of light. So you go for the same spectrum, okay, and this is why we don't have the colour here. Okay, so in a continuous spectrum, we have a red, orange, yellow, green, blue, indigo, violet. If I take a sodium colour, okay, and I don't have the right colour, but for sodium, you don't get any of those. All you get is a couple of yellow lines. Okay, there's only a couple of places there. I'm drawing these in red, but you can see them as yellow. They're yellow, okay? Right, okay, so they're yellow. You get a couple of yellow lines. The amazing thing about spectroscopy is, if it's sodium, you'll always get the same thing. If it's mercury, you'll always get the same thing, but it'll be different to this. It'll be different. They're called fingerprints, okay? They tell you what element that you have excited, okay? So they tell us what's going on. Now, your video later on will show it to you a lot better, okay? And you get an idea. Now, in the video, they talk about absorption spectra as well as emission spectra. We are only interested in emission spectra, okay, for second level. We're interested in all, but what company exam? Emission spectra only, okay, emission spectra only. Okay, it's fascinating, right, okay, but this is one that doesn't work very well on Google Classroom. Okay, when you're doing it in room 4C, whenever we get back to it, you will see this and you say, oh, this is interesting stuff, okay? So that's spectra, okay? So they're the two things we needed to catch up on. I'm now going to go through it in the notes. 2 clips are well worth watching, okay? 2 clips very well worth watching. Experiment 13 done, and then I'll be sending on a kind of a round-up chat later on in the day. Okay, sure I will.